Chapter 2. Continued. Geometry formerly was the chief borrower from arithmetic and algebra, but it has since repaid its obligations with abundant usury. And if I were asked to name in one word the pole star around which the mathematical firmament revolves, the central idea which pervades the whole corpus of mathematical doctrine, I should point to continuity as contained in our notion of space and say it is this. Is this. J. Sylvester. Chapter 1, Part 1. Chapter 2, Part 1. Open and closed sets. The definition of a topological space given in Chapter 1 fits quite well with our intuitive idea of what a space ought to be. Unfortunately, it is not terribly convenient to work with, and our first job is to produce an equivalent, more manageable set of axioms. Let X be a topological space and call a subset O of X open if it is a neighborhood of each of its points. Notice that the union of any collection of open sets is open by axiom C of definition 1.3, and the intersection of any finite number of open sets is open by axiom B. The whole space X is an open set, as is the empty set 0. Also, given a neighborhood N of a point X, axiom D tells us that the interior of N is an open set, which lies inside N and which contains X. In E3, a set is open if each one of its points can be surrounded by a ball which lies entirely inside the set. For example, the half space defined by the inequality z is greater than 0 is open, as is the set of points whose coordinates satisfy x squared plus y squared plus z squared is smaller than 1. On the other hand, the half space defined by z is greater or equal to 0 is not open because any ball, however small, which surrounds a point of the xy plane must dip down into the lower half space given that by 0 is inferior to 0. Z is lesser than 0. The intersection of a finite collection of open sets needs not be open. For example, if we intersect the sets set defined by x, y, z for given that x squared plus y squared plus z squared is lesser than 1 over n, where n is a list of integers greater than 0, we obtain the origin in E3, which is not open. We shall now try to work in the opposite direction, starting from the idea of an open set, then building up a collection of neighborhoods for each point. Suppose then that we have a set X together with a non-empty collection of subsets of X, which we call open sets, such that any union of open set is itself open. Any finite intersection of open sets is open, and both the whole set and the empty set are open. Given a point X of set X, we shall call a subset N of X a neighborhood of X. If we can give an open set O such that X belongs to O and is a subset of N. We claim that this definition of neighborhood makes X into a topological space. Each point has at least one neighborhood, namely the whole set X, and axioms A and C of definition 1.3 clearly hold. If N1 and 2 are neighborhoods of X, we can find open sets O2 or 1 such that X belongs to O1 and is a subset of N1, and X belongs to O2 and is a subset of N2, giving X belonging to O inter O1 inter O2 being subsets of N1 inter N2. But O1 inter O2 is open. Therefore, N1 inter N2 is a neighborhood of X. And we have verified axiom B. Finally, suppose N is a neighborhood of X and let N0 denote the set of point Z such that N is a neighborhood of Z. Choose an open set O such that X belongs to O and is a subset of N. Now O, being open, is a neighborhood of each of its points, so O is contained in N0. Therefore, N0 is a neighborhood of X as required for axiom D. Suppose we go full circle. In other words, we start with a collection of so-called open sets. Construct a topological space X using them. Then, looking at a set, open sets in this space. Do the two notions of open coincide? The answer is yes. For if O is one of the original open sets, then it is by definition a neighborhood for each of its points in X, and therefore an open set of X. Conversely, if U is an open set of X, it is a neighborhood of each of its points. So given X belonging to U, we can find one of the original open sets, say OX, such that X belongs to OX being a subset of U. But then U being defined as the union of OX such that X belonging to U, and is therefore open in the original sense because any union of open sets is open. We leave the reader to check out the other possibility, namely, if we begin with a topological space, introduce the notion of an open set, then construct a family of neighborhoods for each point using these open sets. The neighborhoods which results are precisely those of the original space. The above discussion means we are justified in rephrasing our definition of a topological space in terms of open sets. 2.1 Definition. A topology on a set X is a non-empty collection of subsets X called open sets, such that any union of open sets is open, and any finite intersection of open sets is open, and both X and the empty set are open. A set, together with topology on it, is called a topological space. This is a definition we shall adopt from now on. The open sets of the usual topology on En are characterized as follows. A set U is open if given X belonging to U, we can always find a positive real number, epsilon, such that the ball with center X and radius epsilon lies entirely in U. Whenever we refer to En, we shall have this topology in mind. If we have a topological space X and a subset Y of X, the open sets of the subspace or induced topology of Y are obtained simply by intersecting all the open sets of X with Y. In other words, a subset U of Y is open in the subspace topology if we can find an open set O of X such that U is equal to O inter Y. Any subsets of a Euclidean space picks up a topology from the surrounding space in this way. Whenever we refer to a subspace Y of a topological space X, we shall mean that Y is a subset of X and has the subspace topology. A rather extreme topology is the discrete topology on X. Here, every subset of X is an open set. This is the largest possible topology on a given set X. If one topology contains all the open sets of another, we say it is larger than the other. If X has the discrete topology, we call it a discrete space. For example, if we take the set of points En, which have integer coordinates, and give it the subspace topology, the result is a discrete space. A subset of a topological space is closed if its complement is open. Think of subsets of the plane such as the unit circle, the unit disk, whose points whose coordinates satisfy x squared plus y squared is lesser or equal to 1. The graph of the function y is exponent of x, or the set of points xy such that x is greater or equal to y squared. All these sets are closed. Still working in E2, consider the set A whose points xy satisfy x is greater or equal to 0 and y is structurally greater than 0. This set A is not closed because the x-axis lies in its complement, yet any ball with center on the positive part of the x-axis must meet A. Notice that A is not open either. So, sets may be neither open nor closed. They can equally well be both open and closed. For example, take the space X, which points out those points xy of E squared such that x is greater than or equal to 1 or x is smaller or equal to -1, and whose topology is that induced from E2. The subset of X consisting of those points with positive first coordinate is both open and closed in X, though of course it is not open in E2. We note that the intersection of any family of closed sets is closed, as is the union of any finite family of closed sets. To prove this statement, one simply applies the De Morgan formulae. We can characterize closed sets very nicely as follows. Let A be a subset of a topological space X and call a point P of X a limit point or accumulation point of A. If every neighborhood of P contains at least one point of A negative, the singleton P such that a point may or may not be in A, as the following examples show. Examples. Take X to be the real line are the usual name and notation of E1, and let A consist of the point 1 over n is equal to 1, 2, and so on. Then A has exactly one limit point, namely the origin. Again with x as the real line, take A is equal to the set defined as O 0, 1 with 0 included and 1 excluded. Then each point of A is a limit point of A, and in addition, 1 is a limit point of A. 3. Let x be E3, and let A consist of those points, all of whose coordinates are rational. Then every point of E3 is the limit of point A. At the other extreme, let A be a subset of E3, a superset of E3, B the set of points which have integer coordinates, then A does not have any limit point. Take x to be the set of all real numbers with the so-called finite complement topology. Here is a set. Here a set is open if its complement is finite, or all of x. If we now take A to be an infinite subset of x, say a set of all integers, then every point of x is a limit point of A. On the other end, a finite subset of x has no limit points in this topology. (2.2) Theorem. A set is closed if and only if it contains all its limit points. Proof. If A is closed, its complement x negative A is open, minus A is open. Since an open set is a neighborhood of each of its points, no point of x minus A can be a limit point of A. Therefore, A contains all its limit points. Conversely, suppose A contains all its limit points and let x minus A since x is not limit point of A, we can find x minus A to be a neighborhood of each of its points and consequently open. Therefore, A is closed. The union of A and all its limit points is called the closure of A and is written A with the over score.